All right, in this video, we're going to start talking about related rates. And we're going to start easily with kind of the shifting point between implicit differentiation and related rates problems. And this will be, I think you'll find this a lot easier than the implicit differentiation problems we were doing in the last section. And in just a moment, I think you'll see why. So we're on page 294 in the workbook, and what we're asked to do is to implicitly differentiate the following formulas with respect to time. And what you're going to notice when we look at all of these formulas is that time is not a variable in any of these formulas, which is going to make things a little bit more routine than when we had equations in terms of x and y, and we were differentiating with respect to x. So sometimes we had to use one rule, sometimes we had to use another rule. Since time isn't the variable in any of these equations, we're just going to have one rule to think about when we're doing this. All right, so our first equation here is the surface area of a sphere. And this is that the surface area is equal to 4 times pi r squared, where r is the radius of the sphere. And so differentiating both sides with respect to time, the derivative of a with respect to t is just dA dt. And when we're differentiating 4 pi r squared with respect to t, r is our variable. So 4 pi is a constant. So we've got 4 pi times the derivative of r squared with respect to t, which is 2r dr dt. And we'll clean that up just a little bit. And so that'll be 8 pi r dr dt. And they want us to state what each rate is in the differential equation. So dA dt is what? Well, just kind of reading that, that's the change in area over time. And dr dt is the change in radius over time. And just to give you a little bit of a foreshadowing, this is kind of a neat thing, because what we've got here is we're saying that the area, the surface area of a sphere, depends on its radius. That we knew from back in geometry. But this is saying that the change in area depends on the radius of the sphere and the change in speed of the radius. So that gives us an ability to compare rates, just like we can compute the area and radius itself. Problem 2, and I'm going to go a little bit faster as we go through these. So we've got V is equal to 4/3 pi r cubed. That's the equation for the volume of a sphere. And so differentiating that with respect to time, on the one side, we've got dV dt. And on the other side, we're going to multiply, once again, 4/3 pi is a constant. So we're going to multiply 3 times that. And that's going to be 4 pi times 3r squared. So I'll change that 4 to a 12 r squared dr dt. And once again, dV dt is delta volume, and dr dt is delta radius. So once again, we've got a relationship between the change in the rate of change of the volume and the rate of change of the radius. All right, so now we've got something a little bit trickier. We've got a is equal to the square root of c squared minus b squared, and we're told that c is a constant here. So do you recognize this formula at all? Well, this is a little bit of a rephrasing of the Pythagorean theorem. If we squared both sides and switched b over to the other side, we'd have a squared plus b squared equals c squared. And so we've got a is equal to c squared minus b squared to the 1/2 power. All right, and so dA dt is equal to 1/2 times c squared minus b squared to the negative 1/2 power times the derivative of this with respect to time. Remember, it says that c is a constant, so c squared is a constant, and that just goes away. And so the derivative of this is negative 2b dB dt. All right, and so cleaning that up, the 1/2 and the 2 are going to cancel each other out. And so moving that into the denominator and putting the square root back, I've got b over the square root of c squared minus b squared times dB dt. All right, and here, dA dt. So A and B in the Pythagorean theorem are the lengths of legs of a right triangle, and C is the length of the hypotenuse. So dA dt is the change in one leg over time. This is the last time I'm going to write this down, but you're going to get, I hope you've got the idea. And dB dt is the change in the other leg over time. And both of these are when, so C is constant, so the hypotenuse is fixed. So maybe this is some sort of problem where you've got a ladder sliding down the side of a wall. And so the hypotenuse of the right triangle is going to stay constant because the ladder isn't changing length, but the height of the top part of the triangle is changing, and the distance from the bottom of the triangle to the wall is changing. And so this talks about the relationship between the changes of those two sides. All right, now we've got the volume of a cylinder, V equals pi r squared h. So now R is a constant. So we've got dV dt is equal to, so R is a constant, so pi r squared is a constant. So this is just pi r squared dH dt. And you can think about those two rates yourselves. Next problem is cosine theta is equal to x over 15. All right, so here is a problem where you've got a right triangle and the hypotenuse is fixed and the angle is changing. And as the angle changes, the length of the adjacent side is changing. And so they're talking about, let's come up with a formula that talks about the change in the angle, the rate of change of the angle versus the rate of change of the adjacent side. And so to do that, once again, we're going to differentiate both of these formulas, both sides of the formula with respect to time. So this is something where we're going to use the chain rule. And so this is the derivative of cosine is negative sine of theta. And we need to add a d theta dt to that. And that's equal to 1 over 15 times dx dt. All right, so once again, even though this is not, this is a trig equation, we can still talk about the rates of change between the angle and one of the sides. And the last example here, so they've got the volume of a cone, V equals 1/3 pi r squared h. And they're not telling us that either of these are a constant. So both the radius and the height might change with respect to time. So we've got to factor both of those into the equation. How do we do that? What do we do when we've got two functions that are changing and we want to talk about the effect of the change of multiplying those two things together? We're talking about the rate of change of the product, so we need to use the product rule. So on this side of the equation, we've got dV dt, and over here, we've got 1/3 pi, and maybe I'll just stick all of this in a pair of parentheses. So the derivative of r squared h with respect to r would be 2rh dr dt, and then the change in r squared h with respect, while h is changing, is going to be r squared dH dt. Remember, with the product rule, the first thing you do is we're gonna hold h constant and then take the derivative of r squared, and then we're gonna multiply it by, add it to r squared plus the derivative of h. And we can multiply this out, and we've got now a relationship between the change in volume over time, the change in radius over time, and the change in height over time. All right, so As we're solving these word problems with related rates, being able to implicitly differentiate our key equations with respect to time is going to be an important part of that process. We'll see the whole process starting out in the next video.